Everyone, thanks for joining. I imagine at least a few of us have spent time at the Solar Power International Conference this week and behind on work and needing to catch up. So the intent today is really to talk about an exciting new product launch. I think we can really get through the material in 15 minutes. Certainly any questions we can handle afterwards, but we'll keep this tight, we'll keep it efficient, we'll keep to the high points that again, I think are notably different than any product you've seen from REC to date. So we'll go ahead and get right into it. This is, is this scaling correctly on your screen, Caitlin?
It is not, actually.
I'm seeing just a little tiny piece here.
Is that better?
It's still trying to overblow, I think, the size. Maybe if we just artificially make it smaller, sort of zoom down, that may be a good solution. It's currently at 111. I think if we park it at 100 or 90%, something like that, that might work real well. So let's just go ahead and get into the presentation, and we will be sending out the slides afterwards. So if you can't perfectly see it, that's okay. Again, the idea here is to keep it fairly high level, keep this efficient, and we'll go ahead and toggle to the next slide of the presentation. Really what we're going to be looking at here, the name NPEAK for REC indicates a N-type monocrystalline. The company has had a great reputation over more than 2 decades based off of the multicrystalline value chain. Broad advancements such as multicrystalline PERC, the half-cut cell architecture, all things quite a bit before other vendors. What we have not dabbled in to date is monocrystalline, and of course, REC has had a strong focus with respect to quality and reliability and really owning our value chain and making our own key silicon components. So being deeper into the value chain, of course, means that that is then a bit more expensive and complicated when we switch technology platforms, because we're not just buying cells from another vendor and plugging it into our module line. We're literally making the whole thing. So what we're going to talk about today is the exciting launch of the new NPEAK series. This is the most power-dense module we have ever made to date on a 60-cell form factor. We expect this to reach a maximum in the current design of about 330 watts, with more exciting things to come after that. This is a cell that is manufactured by REC in our Singapore factory. There are some similarities to the current generation of Twin Peak product and some unique advantages as well. That's what the coming slides will show. Again, at a high level, what does this product mean? What are the features and what does it look like? That is a visual depiction on the right-hand side. You'll see the basic module design is quite similar to the current Twin Peak series, meaning that it is a 60-cell form factor with half-cut cells. We've got 2 halves electrically, top and bottom, that are in parallel. We've got some technologies at work here that are reducing cell to module loss, improving partial shaded performance. The notable difference in this product is really twofold. There's one difference inside the laminate, which is of course the cell technology, and there's another difference in the frame design and profile, where we've made some advancements to both increase packing density, increase strength, and really increase the durability of the overall product. These are things that we'll see in just a few moments here. So the bullet points that you see, there's actually a sweet spot within mounting that we'll see a color-coded diagram on, where you can get a very strong snow load rating, clamping in certain areas. And it does have a tighter warranty in terms of power output than the current product, and a longer product warranty. Caitlin, if we can move to the next slide, that'd be fantastic. This is simply a chart showing where it fits into our current product lineup. So we have not yet sunsetted any of the existing technologies, meaning that everything you see on the screen is still in production today. The old non-PERC multicrystalline peak energy product, which was in large-scale deployment in the US for quite a number of years, is today really only sold in other markets in Europe, and in Asia. So that would be the first one to probably leave this picture. But we are still making the multicrystalline PERC Twin Peak 2. There is still the all black variant of that with the reactive ion etch cell. Very beautiful module running around 275, 285. That's the Twin Peak 2 Black 2. This NPEAK slots above it. I think that diagram, which I did not draw myself, is slightly misleading because it seems to indicate a silver colored frame. The US version of this product will have entirely a black frame. The cells, being N-type mono, will be entirely homogeneously black. It will have a white backsheet in its first iteration so we can maximize power output, and then expect to release a black backsheet version later. Of course, that represents the 60-cell side of our lineup. There is also a 72-cell side, which will not yet have the monocrystalline cells, and then some other form factors used in other places around the world. If you're curious, that 50-cell form factor is popular in Japan because they have very small roofs. We have not chosen to bring it here. Don't see it being a good fit for the American market. Let's go ahead and move on to the next slide. As I mentioned earlier, this new N-type mono cell with a PERT technology, and we'll unpack what that means in a couple slides. This is being built at our own integrated facility in Singapore. So this is the facility that we constructed in 2009. We've been manufacturing there for 8 years, extremely proud of the level of automation as well as vertical integration just on one site. Literally, we have the capacity to make ingots, blocks, wafers, cells, modules, all out of that one site. The cool picture indicated by that, the yellow circle and the arrow pointing to it, at our location in Tuas, Singapore, we really had, we had constructed buildings on almost the entire property. There wouldn't be just natural space available to build an expansion. But what we did is moved some of our wafer sawing technology, which for the last years most commonly had been a wire saw that uses a slurry. So there's literally abrasive materials within a slurry compound that goes onto a wire saw. And that's how the wafers are cut from the silicon blocks. But of course, then you get a waste byproduct material of this liquid slurry that then has chemicals in it. It needs to be appropriately treated for environmental responsibility, recycled, and that literally took an entire building at our factory. We transitioned that to the new technology, which is diamond wire. There's no slurry. There's literally bits of diamond, which is a very strong substance, of course, embedded in wire. So there's no need anymore for this slurry recycling facility. We tore that down and built a brand new building, populated it initially with just one pilot line, which is the prudent manufacturing way to do this. You basically design your production line, install one of them, get everything what we call fully debottlenecked, meaning running at the full units per hour speed that it should, make sure that the manufacturing yield, meaning the units that are of appropriate quality to be sold, so not damaged or broken units. And after everything is initially stabilized, then you would look to duplicate that and fan out across additional production lines. So this line is running right now, that started in August, is a pilot line of about 150 megawatts annually. There is enough room in this facility to build additional lines to go somewhere between 600 and 800 megawatts. I actually had an interesting opportunity for updates just in the last 2 days because our Vice President of Technology was visiting us at SPI. So some additional things that are actually not in these slides I'll be able to share. But again, this is not a cell that we are buying externally from someone else. This is our own unique REC design built on an REC production line. Let's go ahead and move on to the next slide, Caitlin. This is a visual depiction of what this looks like. And of course, very clearly you see the half-cut cell architecture here. The interesting update that I had alluded to from our VP of Technology, I'd say not unexpected, because in my 10 years of history with this company, I've known REC to be nothing if not prudent and also conservative. But we're actually getting power output increasing a little faster than we thought. So as opposed to the 2018 production plan that you see at the bottom of this slide, where there's only 40% at 320, we're already seeing about 60 to 70% of these modules coming out at 320 with the ability to add a couple enablers fairly quickly and get up to that 325, 330 level, although that's going to be Q1 deliveries. But this is exciting. This is, again, a brand new cell line. This is a new technology for REC, and we'll look a little bit further into what this means in the next slide. What exactly is this product? I think the background is important because when you look at a module, there are module-specific elements of the design, and then there's, of course, the engine of the module, which is the silicon-based components, the wafer and the cell. How is that being designed? So the things that we've had a lot of success with in recent years, if you recall back to end of 2014 into 2015, that we were the first in commercial scale to introduce half-cut cells. The rest of the industry thought we were a bit crazy at the time, and it couldn't be done at a good manufacturing yield, and debatable whether there were real benefits. And I think time has really told that story, which is if one were to walk the exhibition hall at SPI in the last 3 days, just about every manufacturer at least says that they can do this technology. The amount of vendors that can actually do it in scale, I think, are still just a handful. But that's really a validation, I think, of the R&D of REC and really the viability of that technology. And then since that 2015 year, we also developed a competency in PERC cells. This was on a multi-crystalline format. So this passivated emitter rear cell, it's basically giving your photons a second chance to produce energy if they weren't harnessed on the way into the cell. Also reflects heat. There's associated performance advantages that the industry has grown to really embrace. Does it have to be done the right way process-wise so you don't incur undue light-induced degradation on a P-type product or elevated temperature degradation? Yes, those are all important things, and that's where the manufacturing experience of understanding how to work with passivated emitter type of treatments comes into play. But we are leveraging all of that experience in the past several years for this new N-type product. Now, an N-type product inherently has no light-induced degradation because at a very simplistic level, we are taking the cell base material, the wafer, and we're doping it with phosphorus instead of boron. So it is the boron oxygen impurities that generally cause a susceptibility to LID. So an N-type mono product inherently has no light-induced degradation. If that's worth somewhere between, say, 1.5% and 3% at today's power classes, that's worth something like 7 watts. That's a power class and a half, just that you're not losing from the nameplate rating versus a P-type product. So that's quite exciting. The PERT technology, P-E-R-T, which is slightly misleading because PERC, passivated emitter rear cell, this is basically the N-type mono equivalent, but there's really some words missing in there because the full term is passivated emitter rear cell totally diffused. But if you made an acronym out of that, it would read something like PERCATID, which doesn't really roll off the tongue. In any case, this is very similar in concept to what we've done for years with the PERC treatment, but it is new and unique to the N-type mono. We are still leveraging the half-cut cell layout within the module. This is something that the laser cutting process REC uses. We've become very good at it. We are having the highest manufacturing yield in the industry, meaning we're not incurring cracks and micro cracks. The stringing and tabbing of those smaller cells, we've become quite good at as well. So in terms of reducing cell to module loss, whenever you look at module efficiency ratings, it's always lower than the cell efficiency. So the new N-type mono cells from REC are running between 21.5% and 21.8% efficient. The module is less efficient than that for one reason that we can't do much about, the other reason we can. The one that no one can do much about is what we call the non-productive areas of the module. If you look at the front, you're going to see the front part of the frame. You're going to see backsheet. There's basically areas that are not active PV materials, which subtracts from your module efficiency area if you take the entire footprint of the module. What we can do is really look at minimizing electrical losses. So this is related to the circuitry and busing within the module, and that was really the primary advantage of the half-cut cell architecture. And then, of course, having shading protection on that short side, not just on the long side from bypass diodes, was the other ancillary benefit. So we are combining all of these things, which is why you will see some of these similarities. Does it have a split junction box for the same reason the current Twin Peak 2? Yes, it does. The bus bar design is actually the same. In the future, could that move to a multiple wire type of arrangement? Absolutely. There's a lot that we can do with the technology platform, but REC typically will not, we move incrementally, meaning that we understand the need of our customers to have a highly reliable, high-performing asset in an outdoor environment experiencing very hot temperatures, very cold temperatures, et cetera, for multiple decades. So we tend to move very conservatively, step at a time, and make sure that everything that we are producing is of the quality that folks have come to expect from REC for over 2 decades. Caitlin, why don't we go ahead and move on to the next slide here. So again, stepping back out to the high-level view, now that we know what this product is, what does it look like? I would drill down to just a couple unique features. There's, of course, the signature layout of that half-cut cell design that looks similar to today's product. Biggest difference visually from the front is that the cells are uniform and all black. There was the RIE Black 2 product that also had that feature, but the mainline, say 290 watt Twin Peak 2, had a bluish colored multicrystalline cell. So this does have a different visual aesthetic. And then the other piece, which is fairly interesting, if you look down at the interface, basically the area between cells, you will see a bit of an hourglass shape. So that's not a deliberate reference to a black widow spider or anything like that, but basically the nature of the monocrystalline ingot, when you pull it out, it's in a cylinder. So slicing that into a wafer of about 6 inches square, in order to make the best use of the material, you're not going to have corners. So it's basically the corners of a 6-inch square are in essence cut off, rounded off. So when you arrange them in a half-cut cell architecture, you can either put them the way that you see on your screen, which becomes visually an hourglass, or you could rotate them the other way, and then you get visually a diamond. That's purely aesthetics. Functionally, it would work the exact same way. But again, just kind of unpacking the details, that is what you're looking at here. There are some design goals we had to maintain a very strong performance with module loading, especially in snow load areas. And in any way that we could build the strength and resilience of this module through the behavior that we see when there is loading from wind, from snow, where you basically have a bowing of the laminate. So if you have the most rigid part, which is the frame running around the periphery, that's the outside of the module, would be the strongest mechanical part. There's, of course, the distance in between, which has some flexibility to it. So that's the glass on the front side, EVA on the back side, and everything else, including the silicon cells in the middle. And reducing the flex in that allows for less potential cracks and micro cracks within your cells as the module experiences positive and negative loads through its lifetime. Let's look a little bit further at that in the next couple slides. First, it's important to understand what the cell is, what it does, and how it's made. So are the inherent substrate, this monocrystalline wafer, the N-type design, why would we do this? What we've been doing for 20 years has been extremely well received throughout the world. But of course, the industry is continuing to push its power density, its efficiency, spectral response, energy yield. All these things are elements that we are in constant R&D to improve. So things that we focus on are temperature coefficient, higher absolute efficiency at STC, but also low light performance. Ideally, we would like to contribute as much as we can to speeding up installations. This product initially, because of the 60 cell form factor in the US, is targeted toward residential. It is 1,000 volts DC rated UL, so certainly no reason why it shouldn't be used on commercial applications as well. And let's take another slide and look at some of the more interesting design elements of this module. This is a slide we won't spend a heck of a lot of time. This is basically in words a lot of the things that we've already discussed. Again, a nice thing when you receive it later to go back and say, okay, well, what exactly are these differences? But we can, I think, go on to the next one from here. This is one of my favorite slides because it has really the clearest depiction in layman's terms, or maybe semi-layman's terms, of the construction of the cell on the right-hand side. So basically, this shows the net result of the 10 to 13 individual discrete processes required to make a N-type mono cell from a wafer. There's been a lot of work going on in R&D for a number of years at REC on this. We also leverage the research and development capabilities of an organization called SERIS, S-E-R-I-S, is the Solar Energy Research Institute of Singapore, which is affiliated with Singapore's National University. And of course, being the only PV manufacturer in Singapore, we have a close relationship that really multiplies our R&D assets. So again, the fundamental change is that we're doping this with phosphorus, not with boron. That is the nature of N-type. We're having no LID. We're having a high level of cell performance. We're having the ability to really optimize for better performance at higher wavelengths of light. But that diagram on the right-hand side, if you're really interested in how this stuff is made and the nature of the semiconductor type of material, that's really what you're going to want to look at. So let's go ahead and move on to the next slide here. This is just a very brief one, just reminding us that we're going to have some better degradation. And so there's different degradation modes. There's going to be the light-induced degradation that N-type mono does not have. There's going to be a better annual degradation, and a couple reasons for that. There's a packaging related one, meaning the module design that's related to that. And of course, also being PID free is something that's been important to REC since that came up in the industry as a prime topic of importance back in maybe 2012 or 2013. So these are also factors that are all quite nice. Interesting installation that's vertical on the lower right there. It's maybe not the highest and best use of a PV module, but interesting to look at. Let's go ahead and move to the next slide. Part of the degradation resistance, as I alluded to before, is how can we keep that laminate from flexing? It doesn't have to be immobile, meaning not moving at all, but keep in mind that the element within the laminate that is most sensitive to bending, it's not going to be the EVA, it's not going to be the backsheet, it's not even the glass. Those things will flex repeatedly just fine with no degradation in their reliability. What we need to be careful for is the relatively, perhaps brittle is the wrong word, but for those of you that have actually seen a crystalline wafer or cell, it bends to a degree and then you can get cracks. You can get small versions of cracks, which are micro cracks over repeated movements. And what we are trying to do here is not have the propagation of cracks and micro cracks result in electrically isolated areas of the cell that then do not contribute to the current generation in the module. And that's where you have degradation of performance. So the key here is how do you find a better engineering solution that's still easy to install, that ideally reduces costs, but also increases performance. And what came out of this is actually a frame design that is a little bit thinner than the last generation. So in thickness, the new one is 30 millimeters. The older one was 38 millimeters. But we've then inserted support bars running horizontally. And what that does, it brings back the strength that you would typically lose in reducing thickness by adding that additional structural element, but it also places a great degree of strength and prevention to bowing of the laminate right across that middle of that module, which is the longest span. So it's not just the cell design that helps it result in less degradation here. It's also this resistance to the degradation from mechanical loads. We also get a nice additional benefit of increased packing density. So as module prices drive lower and lower, and some of us having to deal with tariffs these days, that's basically a non-value added cost. The proportional cost of shipping this stuff around the world and on trucks is greater. So what we are trying to do is be able to put more modules in a shipping container, more modules in a truck, and more modules easily in an installation vehicle. Across the whole value chain, there's some interesting benefits here. So that was the purpose. I think we can go ahead and move on from here. We won't drive too much into the details. This is going to look like a bit of an eye chart probably for most of you, but basically if you look at the load ratings versus where the module is mounted. So some folks are using either more or less traditional rail-based systems. There's rail-less systems. There's all sorts of different ways to either attach the module from below using the mounting holes, using top-down clamps, using a universal end clamp. But where it is grabbing the module does have an impact to the strength. So the thing I will point out here is we want to be careful of what's in red. The red areas are basically where you do not want to mount this particular module, where you would have the least strength. You're going to have the most strength in that blue and green area. So any further questions, I advise reaching out to your AE representative and fantastic technical support to really understand what racking products best utilize these strengths. But this color-coded chart is something we started to do to really make that clear, because again, it's not the case that all areas around the rectangle are exactly the same. Let's go ahead and move on to the next one. This is just a very quick, same exact value proposition as the half-cut cell design in the Twin Peak and Twin Peak 2. We are doing the same type of module design, and again, it's worked out extremely well for our customers in both the 60 and 72 cell space. So excited to continue that. Along with less degradation, we have as I mentioned earlier, tighter warranty. I think it's easier to look in a visual depiction in what that means in percentage guaranteed at 25 years, which is 86% versus the old barely over 80. So again, consistent incremental improvements. This is not something that we just increased the number on to keep up with the Joneses or because it felt like a premium positioning should justify that. This is really based off of in-depth cell studies, module studies, actual loading in the real world. So again, something that should constitute a real value for the end customer and system owner. This slide was perhaps the most interesting and surprising when I saw it. What this is an energy yield study. So REC being very pragmatic and wanting to understand the attributes of its own materials as well as those of competitors, what our team did, this was sort of a side project. They wanted to see how our half-cut cell products performed in a real-life situation in terms of energy yield compared to a competitor who seems to be the furthest along in building a half-cut cell. So I won't name the name, but this competitor product, which is the first bar on the left, that is a P-type mono PERC half-cut cell product. I believe it was a 320 watt, but either way, this was levelized to kilowatt hours per watt peak. So again, it wouldn't matter if the power density were different. We're looking at the ability of the module on a per unit basis to produce kilowatt hours of energy. So this was with Ceres, the organization I met before, meaning it is in Singapore. So that's a particular climate, meaning a certain humidity, a certain insolation, et cetera. So I certainly wouldn't say that it's indicative of everywhere around the world. And the results actually ended up being quite a bit more positive than any of us had thought they would be. We are used to seeing our products have a significant energy yield advantage for many years, but we're talking about something on the order of maybe 1, 2, 3%, maybe some cases 4 is the order of magnitude. That's meaningful over the lifetime of a module, but we're not talking about something that is, even close to a double-digit number. That would be unreasonable in the modern market. However, what we saw in this particular case, there's basically, you're looking at 3 different product types. The 2 bars on the right-hand side were 2 NPeak REC units. The one in the middle was our Twin Peak 2, that's a 290 Twin Peak 2, and the one on the left is the competitor's product. So specific energy yield, again, that's levelized, kilowatt hours per watt peak, and there's a total of 5 months actual NALV data, which is more than when the slide came out, and the trending is still the same. We were internally talking about this week, but our NPEAK is running about 8 to 9%. 8 to 9%. That's almost double digits energy yield advantage versus the competitor's product. So again, just a testimony to the work and design expertise we've put into this product. At the end of the day, the litmus test is not a data sheet. It's not even a PTC value. It's really what will the energy yield be in real life conditions? And we're extremely happy and optimistic to see this evidence come in. Let's go ahead and move to the next slide. I think we've only got a couple, and we'll go ahead and wrap up and take some questions. Hey, well, that was a good one to end on.
Yeah.
Thanks, Caitlin.
Well, thank you, Chris. Yeah, no problem. So as always, you can exit the webinar at any time during or following the question and answer session. There will be a survey that will pop up. If you can go ahead and complete that survey, I'll go ahead and get you these slides out to you. And if you, let's see here, we have a few minutes here for, quite a few minutes actually, for some questions. So the first question we have in here is from Graham. His question was, by higher wavelengths, do you mean longer wavelengths or do you mean higher energy, shorter wavelengths?
Great question. So that would be higher energy, shorter wavelengths. So if you look at the visible light spectrum, that observation is actually completely correct, which is longer wavelengths imply lower energy, higher wavelengths, higher frequencies, higher energy. So it would be towards that, the higher end of the scale is where this